Imagine living in a place where the grass is greener but the roads are a puzzle. Welcome to Johnland, where our friend John has a challenge that could stump even the brightest mind. Can you figure out how many unique paths he can take to visit to all his friends without getting lost? Stick around because today we are diving into the world of algorithms and exploring how we can map out this quirky land. Alright, let's dive into the heart of our code and unpack the logic step by step. Imagine we are working on a problem where we need to connect cities in a way that minimizes cost and using roads that comes with different weights or prices. If you will, the goal is to find the total cost of connecting all the cities efficiently. To tackle this, we start by defining what an edge is in our context. An edge connects two cities and has a weight that represents the cost of connecting them. This is where our edge class comes into play. It holds three key pieces of information: the two cities it connects, let's call them U and V, and the weight of the connection. The structure helps us organize our data neatly. Now here's where the magic really happens. We need a way to efficiently manage and merge these connections. This is where the union find data structure or disjoint set union comes into play. Think of it as a way to keep track of which cities are already connected. So when we create our union find class, we initialize two arrays, one to keep track of which city's parent in a connection tree and another to maintain the size of each connected components. Now let's pause here and think about it. Why do we do this? The find function is crucial. It helps us identify which group a city belongs to. If two cities belong to different groups, we can connect them and merge their groups. This is where the union function shines. It not only merges two groups but does it in a way that keeps our tree flat, optimizing future operations. We use the size of the groups to decide which tree should become the parent. This is known as union by size, and it's a smart way to keep things efficient. With our union find structure set up, we can now focus on the main logic. We read the input class, the number of cities, and the number of connections, followed by the specific connections themselves. Each connection is stored in an edge in our list. Here's a critical point. We need to sort these edges by weight. Why? Because we want to connect the cities starting from the cheapest connection to the most expensive. This greedy approach ensures that we minimize the overall cost, and once we have our edges sorted, we initialize our union find structure and set a variable to keep track of the total cost. Now we can iterate to our edges. For each edge, we check if the two cities it connects are already in the same group. If they are not, we can connect them and calculate the cost of that connections. Here's the neat trick. When we connect two cities, we multiply the weight of the edge by the size of the two groups being merged. This gives us the cost of connecting all the cities in those groups, which we add to our total. It's like saying if I connect these two groups, I'm connecting all the current members at this cost. And finally, after processing all the edges, we print the total cost in binary format. This is a small twist that adds a unique flair to our solution. So to recap, we define our edges using a smart data structure to manage connections, sort our edges by weight, and then efficiently calculate the total connection cost while merging groups. This structured approach ensures we are not just finding a solution but doing it in the most cost-effective way possible. Alright folks, let's wrap it up. Today we tackle the Johnland problem from HackerRank, where we efficiently calculated the total weight of all possible connections in a graph. Through our code, we implemented a union find data structure which allowed us to dynamically group nodes and compute the size of each connected components. We sorted the edge based on weights and applied the union operation to connect nodes while ensuring we only counted unique connections. By the end of our solution, we converted the total weight into a binary format for the final output. The key takeaway here are the importance of union find algorithm for handling dynamic connectivity problems and how sorting edges can optimize the process of finding the minimum spanning tree. If you found this content helpful, don't forget to give it a thumbs up. For more coding challenges, and hit that like button and notification bell so that you'll never miss an update. And stay tuned because in our next video, we are going to dive deeper into graph algorithms, like exploring Dijkstra and Prim algorithms and how they can help solve even more complex problems. So you don't want to miss it. And make sure to check the link of the source code in the description below. Happy coding, everyone.